This presentation on testing hypotheses about a mean when the standard deviation is unknown is part 4 of a series of presentations on statistical inference. As in previous programs in this series, the instructional design was developed by David Kleinbaum, statistician, and Anna Washington, educator. The narration was done by David Kleinbaum. We will be using statistical inference to describe how to test a hypothesis about a mean mu. In performing this test, we will make use of information in a sample to draw conclusions about a hypothesized value of mu in a population. The method we will describe for testing hypotheses about mu will involve a 7-step procedure. Although we will focus entirely on the parameter mu, this 7-step procedure is applicable to hypothesis testing questions concerning any parameter of interest, for example, a proportion p, a standard deviation sigma, or any comparisons between two parameters like mu1 minus mu2, p1 minus p2, or sigma1 divided by sigma2. You will be prepared for the material in this presentation if you already have had an overview of statistical inference and now know the essential difference between its two components, hypothesis testing and estimation. Part 1 of this 4-part series has already provided a conceptual overview of statistical inference. Parts 2 and 3 have dealt with methods of estimation using confidence intervals. This presentation on hypothesis testing is part 4 of the series. In this presentation, as in part 3, which considers the parameter mu when sigma is unknown, we'll make use of the student's t-distribution in describing how to test hypotheses about mu. Some preliminary understanding of how the t-distribution differs from the standard normal z-distribution and how to use tables of the t-distribution is therefore a prerequisite. In the discussion to follow, we describe the 7-step procedure for hypothesis testing by way of an example. The testing procedure will then be reviewed by way of a second example. As an example of a hypothesis testing situation, consider a study that has been undertaken to investigate the health of workers in a certain plant suspected of having a heavy toxic environment. Suppose the study is conducted by an independently contracted team of medical investigators, which include a physician, an epidemiologist, an industrial hygienist, and a biostatistician. The team visits the plant for several days and collects a wide variety of information, including a battery of physical examination data on samples of workers from various parts of the factory. Among the many variables measured on the workers in this plant is uric acid level, measured in units of milligrams per 100 milliliters. Suppose that earlier studies at other plants have led investigators to believe that the average uric acid level for workers in the industry is about 6 milligrams per 100 milliliters. Because of the suspected toxic environment of this plant, it is of interest to determine whether the mean uric acid level for the plant is higher than that in the general industry. This question about the mean uric acid level for the plant may be answered by carrying out a statistical test of hypothesis. To operationalize the test situation, suppose, as shown on the lower right, that a random sample of 25 workers considered representative of the plant is studied, and it is found that the sample mean uric acid level is 7.5 and the sample standard deviation is 2.3. Based on this sample, then, can it be concluded that the workers in this plant have uric acid levels higher than those in the general industry? We now proceed to test a statistical hypothesis about the mean uric acid level for the plant by working through each of the 7 steps involved in such a test. The first step requires us to state the information in quantitative terms that will be useful in carrying out the test, and to state the statistical assumptions. To state the information, we will let X denote the uric acid level of a worker in the plant. We therefore have been given that the sample mean X bar is 7.5 and the sample standard deviation S is 2.3 for a sample of N equals 25. We have also been given that the population mean mu for the general industry is equal to 6, and we want to draw a conclusion about the mean mu for the plant. As for the statistical assumptions, it will be necessary in order to carry out a test of hypothesis about mu to assume either that X, the uric acid level, is normally distributed, or that the sample size N is sufficiently large so that X bar has the normal distribution from the central limit theorem. Also, since no information has been provided about the population standard deviation for either the plant or the industry in general, we will therefore assume that sigma is unknown for the plant. You may recall from earlier study or previous presentations that these are the same assumptions required for computing confidence intervals for mu. We now have completed step 1, for which all the pertinent information has been stated. We are now ready to perform step 2, which requires us to state in statistical terms the hypotheses being tested. In general, a statistical hypothesis is any statement concerning the possible value of a parameter of interest, in this case the parameter mu, the uric acid level for the plant. Examples of hypotheses include statements like mu equal to 6, mu is greater than 6, mu is not equal to 6, mu is less than 6, since these are all different statements about the possible value of mu. When performing a statistical test of hypothesis, we must distinguish between two kinds of hypotheses of interest: the null hypothesis H sub 0 and the alternative hypothesis H sub A. In our example, the null hypothesis H sub 0 is that the mean uric acid level mu for the plant is equal to 6, the same value as in the entire industry. In general, H sub 0 describes either what we want to disprove and/or gives the presently accepted state of knowledge about the parameter prior to undertaking the study in question. This is why we have stated H sub 0 as mu equal to 6, since our interest lies in knocking down the hypothesis that the mean for the plant is equal to the mean for the entire industry. The alternative hypothesis H sub A for our example states that the mean mu for the plant is greater than 6. This is called an upper one-sided alternative, and it is not the complete opposite of the null hypothesis. The opposite would be mu not equal to 6, and is called a two-sided alternative, which could include values of mu below 6. We have restricted H sub A to values larger than 6 because the investigators are only interested in detecting whether the workers in the plant are worse off with respect to uric acid level. It is important to emphasize that both the null and the alternative hypotheses must be specified without consideration of the study data. To avoid biasing the conclusions that may be drawn, we must determine the null hypothesis and the alternative hypothesis on the basis of the objective of the study, current theory, or previous research. Thus, we have selected the alternative hypothesis to be mu greater than 6 because, a priori to seeing the data, we are only interested in detecting whether the plant has a higher mean than the entire industry. This choice should not have been determined simply because the sample mean of 7.5 leaned in this direction. In principle, the null hypothesis is treated like the defendant in a trial. It is assumed true or innocent until the evidence makes it highly unlikely to have occurred by chance. Thus, in our study example, we assume in the null hypothesis that the given plant has the same mean uric acid level as in the entire industry, and we evaluate whether the observed results are so unlikely under this null hypothesis that we have to reject the null hypothesis as untrue. Our test procedure is oriented so that a decision is to be made on the credibility of the null hypothesis. If our test results tell us to accept the null hypothesis, then we will be concluding that the observed results were likely to have occurred by chance under the null hypothesis. But if our test results tell us to reject the null hypothesis, we will call our results statistically significant. It is for this latter possible outcome that we have created an alternative hypothesis and have it waiting in the wings. Step 2 is now complete, since our null and alternative hypotheses are determined. The next step requires us to choose alpha, the significance level. In general, the significance level alpha gives the risk of error we are willing to take of rejecting the null hypothesis when in fact the null hypothesis is true. As shown, alpha can usually be described as the area in the tail of a distribution that results when the null hypothesis is assumed to be true. This type of error, usually called a type 1 error, may be made whenever a statistical test is performed. We can, however, choose to make the probability of such error as small as we like in our specification of alpha. For our example, we will choose alpha to be 0.05, which means that we are willing to take a 5% risk of erroneously concluding that the alternative hypothesis is true when in fact the null hypothesis is true. There is no fixed rule for choosing alpha in any given situation. Most investigators, however, typically choose a value between 0.01 and 0.10, depending on how important it is to them not to make the mistake of rejecting the null hypothesis when the null hypothesis is true. In general, the more important it is to avoid such an error, the smaller alpha should be chosen. There is another interpretation of the significance level worth mentioning, which explains why this quantity is so named. In addition to stating the risk of a type 1 error, the significance level alpha also states how rare or unlikely the observed results of one study must be in order to be called statistically significant. To illustrate this interpretation of alpha, suppose we decide before doing the study that if our observed results have less than a 0.05 chance of actually occurring under the null hypothesis, then we would consider such results to be so unlikely that we would reject the null hypothesis in favor of the alternative hypothesis. In other words, the 0.05 value we have specified, which is what we call the significance level, defines precisely how unlikely our observed results must be in order to call them statistically significant. Thus, for an alpha of 0.05, we can say that our result has to have less than a 0.05 probability of occurring under the null hypothesis before we will call it significant. And we can also say that we are willing to take a 5% risk of erring in a conclusion to reject the null hypotheses. Having completed steps 1 through 3, we are now ready to do step 4, which requires us to select the test statistic to be used and to state its distribution under the null hypothesis. Step 4 involves determining the test statistic, which is the form of measurement upon whose value is based the decision to reject or not reject the null hypothesis. For example, if the value of the test statistic based on the sample is high, which suggests a high toxic environment, we may decide to reject the null hypothesis. On the other hand, if the value of the test statistic is not unusually high, this would suggest not rejecting the null hypothesis, thereby concluding that the plant is not unusually toxic, at least with regard to uric acid level. Deciding on the specific mathematical form that any test statistic takes, whether, for example, it is the familiar z or t variable, or some other kind of variable like an f or chi-square, depends on the parameter of interest and on the statistical assumptions being made. Our parameter of interest has been mu, but others that might be considered in different problem situations include mu1 minus mu2, sigma, sigma1 over sigma2, p, or p1 minus p2. The assumptions we have considered include whether x or x bar is normal and whether or not sigma is unknown. Other assumptions may have to be considered for different parameters of interest. Since our problem situation considers testing a hypothesis about a population mean when the population standard deviation is unknown, the test statistic we must use is given by the general form t equals x bar minus mu sub 0 divided by s over the square root of n. Here, mu sub 0 denotes the hypothesized value of the population mean under the null hypothesis, and as before, x bar, s, and n denotes the sample mean, sample standard deviation, and sample size, respectively. This test statistic t, which is shown again here, has the t-distribution with n-1 degrees of freedom under the null hypothesis, provided that we can assume that either x, our underlying uric acid level variable, or x bar, the sample mean of x's, is normally distributed. If sigma had been known, we would have used a standard normal or z variable as shown above. However, since sigma is unknown, we must use a t variable, which uses s instead of sigma in its denominator. For the example we have been discussing, the hypothesized value of mu equals 6, the same as the mean for the general industry. Thus, our test statistic for step 4 is of the specific form t equals x bar minus 6 divided by s over the square root of 25, which has the t-distribution with n-1 equals 24 degrees of freedom under the null hypothesis. Since our test statistic follows the t-distribution with 24 degrees of freedom under the null hypothesis, we can obtain percentage points of this statistic from tables of the t-distribution, such as the one provided to you at the back of your viewing study guide for this presentation. This table will therefore need to be consulted when constructing the decision rule for our test, which is the next step to be described. Step 5 of our hypothesis testing procedure requires us to explicitly state, in terms of the test statistic, the decision rule that will be used to decide whether or not to reject the null hypothesis, h sub 0. In specifying the decision rule, we must partition the possible outcomes of the study, as represented by different values of the test statistic t, into two regions called the acceptance and rejection regions. If the observed study value falls in the acceptance region, we will decide not to reject the null hypothesis. However, if the observed study value falls in the rejection region, we will decide to reject the null hypothesis. Note that when the observed value falls in the acceptance region, in the spirit of a court trial, we don't really accept the null hypothesis, but rather we lack evidence to reject it. The particular decision rule to be used will depend on the specific form of alternative hypothesis h sub a being considered, the value of the significance level alpha, and the distribution of the test statistic under the null hypothesis. Three types of rejection regions are contrasted here. At the top, we have what is called an upper one-tailed rejection region, for which values of t only in the upper tail of the distribution under the null hypothesis will lead to rejection. The form of the rejection region is therefore stated as t greater than or equal to c. where C denotes the critical point or value of the test statistic that separates the acceptance from the rejection region. In the middle, we have illustrated what is called a lower one-tailed rejection region, for which values of t only in the lower tail of the distribution under h sub 0 will lead to rejection. The form of the rejection region here is thus t less than or equal to c. At the bottom, we have what is called a two-tailed rejection region. Notice that for this decision rule, the significance level alpha has been split into two tails of the distribution in contrast to the one-tailed tests above. For a two-tailed test, we will reject the null hypothesis if the value of the test statistic falls either in the extreme lower tail or in the extreme upper tail of the distribution. To identify these tails precisely, we need to determine two critical points, C sub 1 and C sub 2. The rejection region can then be written as t less than or equal to C sub 1 and t greater than or equal to C sub 2. The decision rule for our uric acid example turns out to give an upper one-tailed rejection region involving a percentage point of the t-distribution. This is because our alternative hypothesis is upper one-sided. The critical point which separates the rejection region from the acceptance region is the percentage point t sub n minus 1, 1 minus alpha. Our decision rule is thus stated as follows. We will reject the null hypothesis if the computed value of the test statistic t is equal to or greater than the 1 minus alpha percentage point of the t-distribution with n minus 1 degrees of freedom. We'll accept the null hypothesis, or at least do not reject the null hypothesis, if the value of t lies below this same percentage point. Using our sample size n equal 25 and our significance level alpha equal to 0.05, the critical point t sub n minus 1, 1 minus alpha turns out to be t sub 24, 0.95, which is found in the table to be 1.7106. Thus, the decision rule for our test specifies that we will reject the null hypothesis if the value of our test statistic t exceeds 1.7106, and we will not reject otherwise. We have completed the first 5 steps of our hypothesis testing procedure. The steps and their results are summarized here. They are: 1. State the information and assumptions. 2. State the hypotheses. 3. Choose alpha. 4. Select the test statistic. And 5. State the decision rule. We will consider the last 2 steps one at a time. Step 6 requires us to compute the value of the test statistic from the observed data. For our example, to distinguish the computed value of t from the variable t itself, we will denote the computed value by t star. To carry out step 6, we simply substitute the values of x bar equal to 7.5, s equal to 2.3 into the test statistic formula t equal to x bar minus 6 divided by s over the square root of n to obtain the computed value t star equals 7.5 minus 6 divided by 2.3 over the square root of 25, which equals 1.5 divided by 0.46, which equals 3.26. So much for step 6. We are now ready to carry out the last step, which requires us to make a decision and draw our conclusions for the test. In doing this, we will reject the null hypothesis if t star falls into the rejection region defined from our decision rule, and we will not reject the null hypothesis otherwise. As illustrated here, the computed value t star equals 3.26 exceeds the critical point 1.7106 and therefore falls into the rejection region for our test. We therefore conclude that we reject the null hypothesis at alpha equal to 0.05, or in other words, our observed results are statistically significant. In drawing conclusions for our test, it is important that we try to state our decision in terms of the particular problem situation we are considering. In our particular example, we can therefore state that the mean uric acid level of the plant is significantly higher at the 0.05 level of significance than the mean uric acid level for the entire industry. In interpreting this statement, the expression significantly higher refers to the fact that we have drawn our conclusions on the basis of the 7-step procedure we have just outlined. Here we present a summary of all 7 steps of our methodology. Reviewing the steps in order, we must first state the information provided and the assumptions made about the underlying data and parameters being considered. Second, we state the null and alternative hypotheses. Third, choose the significance level alpha. In step 4, select the test statistic and state its distribution under the null hypothesis. Step 5 requires us to determine our decision rule, usually given by a formula or picture which identifies the rejection region. We then compute T star, the value of the test statistic from the observed data. And finally, we make a decision and draw our conclusions according to whether or not T star falls into the rejection region. We have finished applying the 7 steps of hypothesis testing to the example of uric acid levels in the plants suspected of having a toxic environment. We are now ready to review this procedure by way of a second example, which is summarized in your viewing study guide as the practice problem. Before proceeding further, you may wish to take a break. When you are ready to continue, proceed to the next slide. We are now ready to continue our presentation by way of the second example. Consider a study that has been conducted to compare 2 approaches for improving the behavior of emotionally handicapped children living in group homes in North Carolina. One collection of group homes across the state has been using a behaviorist treatment approach on their children. Another set of homes has used instead a re-educational treatment approach. The question of interest, therefore, is whether or not there has been a difference in the effect of these 2 approaches on the children's behavior. To compare the 2 approaches, our study has been designed so that for each child randomly selected from a group home using the behaviorist approach, a corresponding child of the same age, race, sex, length of residence, and type of problem was selected from a group home using the re-educational approach. Statistically, we call this a matched pair study, since children receiving different treatments have been paired up on characteristics that make each pair a good match. In collecting the data for this matched pairs design, an index or score has been computed for each child in a sample of 15 pairs. This index measures the behavior change score X during the child's period of residence in the home. Thus, the study data consists of a collection of 15 pairs of behavior change scores on 30 different children, where one child in each pair has received the behaviorist treatment while the other child in the same pair has received the re-educational treatment. As shown here, we have used different subscripts to distinguish the X scores for a given child within a given pair. For example, X sub B1 denotes the X score for the child in the first pair that came from a behaviorist home, whereas X sub R1 denotes the X score for the other child in the first pair from a re-educational home. And here is the data that was collected for each of the 15 pairs of children studied. We are now ready to consider how to use this data to test a statistical hypothesis about a population mean. However, before we can carry out our 7-step procedure, we must be able to transform our data from pairs of numbers to a single set of numbers. For any matched pairs design, we can easily transform our data by taking the difference within each pair, which we have done in the last column on the right. We now have a sample of 15 difference scores, one for each pair, and we can use the sample mean difference score to test a hypothesis about a single population mean difference score. To simplify our notation, we will denote the difference for each pair by x sub d. For the 15 difference scores of our sample, we can then compute the sample mean x sub d bar to be 2.86 and the sample standard deviation s sub d to be 3.563. Note that the sample mean difference certainly is greater than 0. Since the difference score for any pair is defined to be the behaviorist minus re-educational score for that pair, this suggests that the behaviorist approach has a better effect on the emotionally disturbed child than the re-educational approach. Nevertheless, we have only used the sample of 15 pairs to get this result. We would therefore like to know whether this result would have occurred by chance under the null hypothesis, which we will determine by our statistical test. We are now ready to proceed through our 7-step testing procedure. For the first step, we can state the following information. Our variable is x sub d, the difference in behavior change scores. We have a sample of n equal 15 such scores for which x sub d bar equals 2.86 and s sub d equals 3.563. Our parameter of interest is mu sub d, the population mean difference scores for all pairs of children that can be formed from group homes in North Carolina. Since our sample size of n equal 15 is rather small, we will have to assume that the variable x sub d is normally distributed, although if this is not true, our test results may be invalid. We also assume that sigma sub d, the standard deviation of difference scores, is unknown. Step 2 requires us to state the null and alternative hypotheses. Since our main question of interest concerns whether or not there is a difference between the effects of the two group home approaches, the null version of this question is that there is no difference. Thus, our null hypothesis should be stated as mu sub d equals 0. As far as the alternative hypothesis, we must state it as mu sub d not equal to 0, since no a priori indication has been given in our problem description that any one of the two approaches used is expected to give better results. Notice that this form of alternative hypothesis is a two-sided one in contrast to the upper one-sided alternative considered in our uric acid example. Our next step requires us to choose alpha, the significance level. We will use a different alpha than before, this time 0.10. Note that an alpha of 0.10 is larger than the previous alpha of 0.05, which means that we are now willing to take a larger risk, 10%, instead of 5%, of rejecting the null hypothesis when the null hypothesis is true. We are also saying that our observed results must have less than a 0.10 probability of occurring under the null hypothesis in order for us to declare them statistically significant. Step 4 requires us to select our test statistic. Since, as with our previous example, we are testing a hypothesis about a single mean, our test statistic is of the form t equal to x bar minus mu sub 0 divided by s over the square root of n, where in this case our mu sub 0 is 0, the value of mu sub d under the null hypothesis, and our n is 15. Under the null hypothesis, this test statistic will have the t-distribution with n-1 or 14 degrees of freedom. Step 5 requires us to state our decision rule, which identifies our acceptance and rejection regions. Since our alternative hypothesis is two-sided, this rule will have to be two-tailed. This means that we need to determine two critical points, C sub 1 and C sub 2, which identify the rejection region as comprising values in each tail of the null distribution, and the acceptance region as a set of values in the center of the distribution. To determine the two critical points, C sub 1 and C sub 2, we must make use of the significance level alpha, which is 0.10. We have to split up alpha equally with the two tails of the distribution so that the area in each tail is 0.05. The critical points can then be identified as percentage points of the distribution of t under the null hypothesis, which is students t with 14 degrees of freedom. These percentage points can then be determined by using a table of the student's t distribution. The degrees of freedom to look up is 14, since our test statistic has the t distribution with this degrees of freedom under the null hypothesis. The percentage point to look up is t 0.95, 1 minus the 0.05 area in the upper tail. The upper tail percentage point is thus 1.7613. Using the symmetry of the t distribution, the lower tail percentage point is minus 1.7613. The rejection region can be defined by the two statements, t less than or equal to minus 1.7613 and t greater than or equal to 1.7613. An equivalent mathematical expression for the rejection region is the absolute value of t is greater than or equal to 1.7613. Thus, our decision rule states that if the value of the test statistic either lies below minus 1.7613 or exceeds 1.7613, we should reject the null hypothesis. Otherwise, we should not reject the null hypothesis. We have now completed steps 1 through 5 of our matched pair study to compare two treatment approaches used by group homes. Step 6 involves computing t-star, the value of the test statistic using the observed data. In step 7, we make a decision or draw conclusions about whether to reject or not reject the null hypothesis depending on the value of t-star. You may carry out these last two steps on your own. To review this hypothesis testing problem about mu, see the description of example 2, the practice problem, in your viewing study guide. We have left space for you to complete steps 6 and 7, but we have also provided the answers to this practice problem on the following page. After you complete this problem, you should then take the post-test which follows the viewing study guide that accompanies this program.